Hello, Math 201. Welcome to this lecture on section 3.1, Intro to Derivatives. And so this is the main topic of Calc 1, derivatives. And so we're going to talk about these things for the next 5 to 6 weeks. It'll be the main kind of bulk of this course. And so all the work we did with limits is to define this thing called the derivative, which is what one of the most important things we're going to learn is. And so let's dive into it. And so remember, derivatives are really greatly related to the slope of the tangent line. That's how we define a derivative. And the reason why these things are related is because they both tell us the instantaneous rate of change. Or remember when we were talking about the velocity, it's the instantaneous velocity of an object. So IROC is what we call instantaneous rate of change. So here's the idea. If you have some function, f of x, and you want to know how quickly it's changing at an instant, that is the slope of the tangent line. And you can do it at different points along the function. If I did it at this point, the slope will be down and to the right, so down and to the right. And so it's a negative slope, and so the function is decreasing or getting smaller. If I do it right here, it's going up and to the right, and so, or up and to the right. And so because of that, it's positive slope, and so it's increasing. Tangents give direction of motion. And so this tangent line tells us that it's moving in that direction. This tangent line tells us moving in that direction, moving in that direction. And they give us, and we can kind of use tangent lines to tell us kind of what the trajectory of an object would be. And so how tangent lines are related to functions, they're all very interconnected. And the idea is that the derivative is the number, or this is how you calculate this slope of that tangent line. Okay, so let's recall the example with instantaneous velocity. So remember, instantaneous velocity is the slope of the tangent line is the limit as t approaches a. So as this number gets closer and closer to a, this secant line will get closer and closer and will eventually become the tangent line, because the average velocity in secant line is just s of t minus s of a over t minus a, which is the slope of that line. And if you take the limit as t goes to a, then the slope of the secant line becomes the slope of the tangent line. And the idea is that s of t is the position function, but we could do this with any function f of x. And then the slope of the tangent line and the slope of the secant line still mean the instantaneous rate of change and average rate of change of f of x. So the slope of the tangent line still will tell you what the instantaneous rate of change is, and the slope of a secant line will tell you what the average rate of change is of your function. And the idea is that as the x gets closer and closer to a, the slope of the secant line gets closer and closer until it becomes the slope of the tangent line. And the slope of the tangent line, that thing that we're going to define, that slope, that is the derivative. And so the slope of a secant line between x and a is just given by the slope formula, right? It's f of x minus f of a, so the change in y, over the change in x, which is x minus a. And so that's the slope of the secant line. The slope of the tangent line is just the limit as we take the value x and get closer and closer to a. Technically, you should be able to approach it from both sides, but generally we draw the picture just approaching it from one side. But if you approach it from the other side and drew secant lines over here, they would still approach the same thing. And so the slope of the tangent line is given by a limit. And we can actually find the equation of the tangent line at x equals a because we have a slope, right? Oops. We have a slope right here. If we have a slope and we have a point, right? The point right here is a comma f of a. So this point right here is a comma f of a. We have a point, we have a slope. We should find the equation of a line. So the way we can find the equation of a line is by using the point slope form of a line. And so if you have a slope and you have a point, then the equation of the line is just y minus the y value of your point. And you set it equal to the slope m, and then times in parentheses x minus the x value of your point. This is the easiest way to get the equation of a line from a slope and a point. And so that means we can find the equation of a tangent line very easily. So that means the equation of a tangent line at x equals a is just y minus the y value, which is f of a, and you set it equal to the slope of the tangent line times x minus a, where the slope of the tangent line is the limit of that. And so let's put all this together and do an example. Find the equation of a tangent of the line tangent to the graph f of x equals 3 over x at the following point. And so we have a point. So our point is 2 comma 3 halves, right? Where 2 is our a value and 3 halves is what happens when you plug in 2 into the function. Now we need the slope. And so the slope is the slope of the tangent line. And remember that is defined to be the limit as x approaches a, well, x is 2, of f of x, which is 3 over x, minus f of 2, which is 3 over 2, over x minus 2, which is x minus a, right? That's the slope of the tangent line. Because remember, it's the, let me get it right here. Where does that come from? Because the slope of the tangent line is equal to the limit as x approaches a. And so a in this case, a is equal to 2, and f of x is equal to 3 over x. And so plugging in those things right here, we get this. And now how do we take this limit? Well, if you tried plugging into, you get 0 over 0, which is indeterminate. And so we need a factor. And so, or not factor, we need to combine like terms. And so doing a little bit of algebra, this becomes the limit as x approaches 2. And then how do we combine those fractions into one fraction? Well, you find a common denominator. And so I need to multiply by 2, multiply by x. And so I get 3 times 2 over 2 times x minus 3 times x over 2 times x all over x minus 2. And then what does that equal? Well, that equals the limit as x approaches 2 of 6 minus 3x over 2x divided by x minus 2. But then when you have a fraction over a fraction, that's the same thing as multiplying by the reciprocal. So this is the limit as x approaches 2 of 6 minus 3x over 2x. And then times 1 over x minus 2. But you'll notice that if I pull out a 3 here, that those will cancel. And so this equals the limit as x approaches 2, 3 times, and then just, actually I need to pull out a negative 3 to make it so that it matches, right? I have to pull out a negative 3 so that that matches that. Because what's left over when I pull out a negative 3 is x and then minus 2. And then all over 2x and then times 1 over x minus 2. And now that cancels with that. And so this becomes the limit as x approaches 2 of negative 3 over 2x. And now I can plug in 2 because it will not make the bottom 0. And so this equals negative 3 over 4. And so the slope of our tangent line is negative 3/4. And so we have a point. Let me remind us what the point is. It's 2 comma 3 halves. 2 comma 3 halves. We have a slope, and our slope is defined to be negative 3/4 because we found it. And so the equation of our tangent line is just y minus 3 halves is equal to our slope, negative 3/4 times x minus 2. And that's totally fine. You could just leave it like that. But if you want to put it in y equals mx plus b form, that's not hard. We just distribute it and you get y equals negative 3/4 x, and then plus 3 halves by distributing that times that gives us plus 3 halves, and then minus, and then plus another 3 halves from the other side. And so this will be negative 3/4 x plus 3, because 3 halves plus 3 halves is 3. And so that's what we get. And so that is the equation of our tangent line. Maybe I'll rewrite it. So y equals negative 3/4 x plus 3. That is the final answer. And to kind of show the picture of what's going on here, here's the function y equals 3 over x. Here's the point 2 comma 3 halves. The slope at that point is negative 3/4 and it includes that point. And so the equation of the line is negative 3/4 x plus 3. So that's the tangent line to the function. And so that was how we do it using this kind of formula, f of x minus f of a over x minus a. But there's actually another way we can calculate the tangent line, thinking about it slightly differently. So replacing x with instead a plus h. So the quantity that we want to keep track of is the distance between these 2 points, calling that h. Then the slope of the tangent line becomes the limit as that quantity goes to 0 of f of a plus h minus f of a over h. And so this actually turns out to be a nicer quantity to calculate for a lot of functions. And so that's why we choose to use this form to calculate it. And so this is the new slope of the tangent. Both of them are true. So you can do the limit as h approaches 0 or the limit as x approaches a. Either one is fine. They'll give you the same answer. Sometimes the calculus is easier, or the calculating is easier with this. So let's do an example. So find the equation line of the line tangent at 1, 5. So our point is going to be the following. It's 1, 5. And our tangent line slope, by using the definition, is the limit. Let me say that limit as h approaches 0 of f of a plus h. And so if I plug in 1 plus h into here, what do I get? I get 1 plus h cubed plus 4 times 1 plus h, because that is f of 1 plus h is 1 plus h cubed plus 4 times 1 plus h. And f of 1, if you plug in 1 into that, is just 5. And so it's that minus f of 1, which is 5, all over h. And so I want to take the limit as h goes to 0. And you'll notice if you just try and plug in h equals 0, that will become 5 and then minus 5 over, and you get 0 to 0. So we need to do something a little bit more. We need to do some algebra. So we need to FOIL this out. And so I will do it like this. I'll do 1 plus h and then times 1 plus h squared, which is 1 plus 2h plus h squared, if you take those two, and then plus 4h minus 5 all over h, and it's the limit as h approaches 0. Don't want to forget that limit. And then now we can FOIL this guy to that, and what do we get? We get 1 plus 2h plus h squared plus h plus 2h squared plus h cubed plus 4h minus 5 all over h, and it's the limit as h approaches 0. So a lot of things are going to cancel now. That will cancel with that and that. Then what else? We should get the limit as h approaches 0 of 3h, I believe. 3h plus 3h squared plus h cubed all over h. Now every term has an h in it, so we can cancel. Comes a 2. And now we can, so this is equal to the limit as h approaches 0 of 3 plus 3h plus h squared. Now we can set h equal to 0, and so this equals 3. And so the slope of our tangent line is 3, and then the point is 1, 5, and so we have a point. So our point is 1, 5. Our slope is going to be equal to 3. And so now our equation of our line is y minus 5 is equal to 3 times x minus 1. Again, if you like it better in y equals mx plus b form, this is 3x minus 3 plus 5. And so this is 3x plus 2. And so y equals 3x plus 2. That is the equation of our tangent line. It has slope 3, and it has the point 1, 5 in it. And so that's how you find the equation of a tangent line, using a formula with h going to 0 instead of x going to a. And now that we've calculated some tangent lines, we're actually ready to give the definition of the derivative. And it is precisely this equation right here where we found the slope of the tangent line. And so let's just define it. So the derivative at a point definition, the derivative of a function at a point. Oh, that's all to say the same thing, right? So the derivative of f at a denoted f prime of a. So f prime of a is f prime of a is given by either of the following two limits, provided the limit exists and a is in the domain of f. So we can only do this if this limit exists and if the value is in, you can actually plug it into the function. If this value exists, the slope of the tangent line, if it exists, we say that f is differentiable at a, meaning that you can actually find the derivative at that value. And so the key is this, that the slope of the tangent line is defined to just be f prime of a. So the derivative really is just the slope of the tangent line, and it's given by these limits. And more often than not, we'll probably use that limit, although this one has its important calculations too. And so key point, f of x is a function, then f prime of a tells us the slope of the tangent line at x equals a, which is the instantaneous rate of change at x equals a. So it's how quickly the function is changing at that given value. So now that we have all that in tow, let's do one final example. So derivatives and tangent lines. Let f of x equal square root of 2x plus 1. Compute f prime of 2, the derivative of f at x equals 2, and use the result to find an equation of the line tangent to the graph. So now with our new formula, f prime of 2 is the limit. And for this particular one, either form will be fine, but let's do the h approaches 0 formula. It will be the limit as h approaches 0, f of 2 plus h, which is square root of 2, and then in parentheses, it's very important that we have that in parentheses, plus 1, and then minus f of 2, which is the square root of 2 times 2 plus 1. That's in parentheses 2 because we're subtracting the whole thing. And then all over h, because this right here is f of 2 plus h, and then this right here is f of 2, right? And so that's where the formula comes into play. So what is this equal to? This is the limit as h approaches 0, and then this becomes the square root of 4 plus 4h plus 1 minus the square root of 2 plus 1, which is going to be the square root or square root of 4 plus 1. So it's 2 plus 1. So this is minus 3 all over h. And so what is that? That's the limit as h approaches 0, square root of 4 plus 4h minus 2 all over h. And so if you try and plug in h equals 0, you'll get 2 minus 2 over 0, so 0 over 0. And so we're going to have to do something else. Because there's a square root here, I think the best thing to do would be to multiply by conjugate. So multiply by conjugate because of the square root. That's why we're going to do that. And so this equals the limit as h approaches 0 of square root of 4 plus 4h minus 2 times the conjugate, which is the square root of 4 plus 4h plus 2, all over h times the square root of 4 plus 4h plus 2. Okay, now let's FOIL that all out. What do we get? The top will just become 4 plus 4h because, and then minus 2 squared, which is minus 4, and then all over h. It's the limit as h approaches 0. That's a 0. Limit as h approaches 0, and then I'm not going to do anything with this. I'll just leave it as 4 times plus 4h square root plus 2. And then something really nice happens. That cancels with that. And then that cancels with that because it's just a 4h on top. And so the h's cancel. And so we're left with something that simplifies really nicely. This becomes the limit as h approaches 0. And then it's 4 on top now. And then on the bottom, it's square root of 4 plus 4h plus 2. But now we're in position to plug in 0. And so if you plug in 0, this becomes 4 over square root of 4 plus 2. That just equals 1. And so f prime of 2, so f prime of 2 is just equal to 1. So the slope of the tangent line at x equals 2 for this particular function is 1. And our point is the point 1 comma f of 2, which is equal to 1 comma, if you plug in 2 into the function, it was 3. So this is our point. I'll do it in purple. So this is our slope. This is our point. And so the equation on the tangent line. So equation of a tangent line is just going to be, just plug in, it's just y minus the y value 3 is equal to the slope 1 times x minus the x value 1. And so again, if you want to write this, this is x minus 1, and then you add 3, and so y is equal to x, and then if you add 3, it'd be plus 2. And so that is the equation of our tangent line. And so in general, we actually have a new form of the tangent line. So equation of a tangent line in general, equation of tangent line at x equals a, now in general, is going to be y minus f of a is equal to f prime of a times x minus a. So this is the new formula using the prime notation, the derivative notation. All right, and so that should be all you need to do this section, and I'll see you guys next time.